Hold a piece of solid gallium in your bare hand, and your body heat will melt it into a silvery puddle. While it is safe to touch, bringing even a few drops of this liquid onto a commercial aircraft is a federal violation. Gallium has a melting point of just 85.6 degrees Fahrenheit. It is non-toxic and does not react with human skin, which makes its strict prohibition in aviation seem like an overreaction. However, the ban exists to protect the aircraft itself. Most commercial plane hulls are constructed from lightweight aluminum alloys, materials that are uniquely vulnerable to gallium. If you place a drop of gallium on a solid aluminum padlock or a soda can, the metal begins to fail almost immediately. Within minutes, the rigid structure breaks down and can be crumbled by hand. This safe, room-temperature liquid can destroy the structural integrity of a solid metal object, reducing high-strength aluminum to the consistency of wet chalk. This rapid degradation is a phenomenon known as liquid metal embrittlement. Unlike rust or acid damage, this is not a chemical reaction. The gallium isn't eating the aluminum, it is a physical invasion. The exterior of the aluminum often looks completely unchanged until it is touched. Only then does the metal give way, resulting in sudden, catastrophic cracking. The danger of liquid metal embrittlement is its stealth. It is an invisible physical sabotage that dismantles the metal from the inside out. To see how this happens, we have to look at aluminum at the microscopic scale. A solid block of the metal is actually a mosaic of billions of microscopic crystalline grains pressed tightly together. When liquid gallium touches the surface of the metal, it acts exactly like water seeping deep into the tiny cracks of a dry pavement. It continuously infiltrates the microscopic boundaries between the aluminum grains. In this microscopic view of an aluminum alloy, you can see this structure in detail. The blue areas identify the intergranular boundaries, where the gallium enters, leading to the severe damage marked in red. This spectral scan provides the evidence. Bright teal horizontal traces are gallium, showing where the liquid metal settled inside the aluminum. It doesn't attack randomly. It precisely targets and saturates the pathways between grains, exploiting the boundaries that hold the aluminum together. At the atomic level, gallium wedges into these boundaries, replacing strong aluminum bonds with weaker aluminum-gallium bonds. Normally, grains slide past each other, allowing the metal to bend. Now that ability is lost. Instead of flexing, the grains separate and the material shatters. As these internal cracks spread, they expose the raw interior of the metal to the air. This scan shows oxygen, represented by these purple clusters, rushing into the fractures and saturating the damaged zones. This microscopic invasion forces a total shift in how the metal behaves. High-strength aluminum is transformed from a ductile, bendable material into one that is entirely brittle, fracturing without warning. Once the process is complete, the aluminum has been converted into a weak, flaky substance called al-gal alloy. This alloy is also chemically compromised. Pure aluminum stays stable because it forms a thin skin of oxide that protects it from the environment. Gallium prevents this skin from sealing, leaving the aluminum raw and reactive. If this material touches water, it will trigger a chemical breakdown that releases hydrogen gas. If a gallium spill occurs in an aircraft cargo hold, the liquid seeps into the structural framing. As it migrates through the floor beams and hull supports, it can cause a localized structural collapse of the airframe. The FAA's strict packaging rules are not an overreaction. They are the only line of defense preventing a small volume of liquid from compromising a plane mid-flight. Despite its destructive power, liquid gallium is highly valued by engineers. Under the right conditions, its extreme density and thermal conductivity make it an ideal tool for advanced technology. It is frequently used as a thermal interface for computer hardware, where it replaces traditional pastes to help cool high-performance, overclocked processors. NASA has even explored using gallium when designing thrusters for deep space, taking advantage of its efficiency as a liquid propellant in electromagnetic accelerators. To use it safely, engineers must isolate the liquid inside materials that are immune to embrittlement, like 316L stainless steel. This ensures the gallium never comes into contact with aluminum components. Our ability to push the limits of modern aerospace and computing depends on our ability to control this paradox. A room-temperature liquid that can empower our most advanced machines, or effortlessly destroy them from the inside out.